For hierarchical clustering, let's focus on the agglomerative or bottom-up approach. Recall that the key operation here is to repeatedly combine two nearest clusters. And to do this, we have three important questions. The first one is, how do you represent a cluster of more than one point? Because you want to combine clusters, right? Not just points. And the second question is, how do you determine the nearness of clusters? Because you need to decide which clusters to combine. And the third question is when to stop combining clusters. For the first question, which is how to represent a cluster of many points, the key problem is, as we merge clusters, how do we represent the location of each cluster, basically to tell which pair of cluster is the closest. And in a Euclidean case, this is much easier because for each cluster, we can use the centroid to represent the cluster. And we define the centroid as the average of all of its data points. And for the second question, how to determine nearness of clusters, since we already decided to use the centroid to represent each cluster, we can just measure the cluster distances using the distances between centroids. Let's say that, for example, we have 6 data points and we want to perform a hierarchical clustering. And this is the 6 data points here. And at the first step, we will look for the closest pair of data points, which is these two. And these 2 points will form a cluster. And then we will compute that corresponding centroid, which is here. And we will look for the next closest pair of clusters, which is these two. And we will compute its centroid. Similarly, we will look for the next pair, and we expect the next pair of clusters to be the pair of clusters with the smallest distance, and it happens to be this cluster. And at this point, we will have 3 points together forming a larger cluster, and we will compute the average of these 3 points as the new centroid. And this process will go on, and we will compute the new centroid of this second large cluster. So when is the best time to stop? Of course, you can just go ahead and merge these 2 largest clusters, but then it will be meaningless because it will just be one cluster containing all the points. So usually, one idea is to record the average distance to the centroid along the time you're performing this algorithm. And the best time to stop is that when you see a dramatic increase of the average distance. And in this case, it's probably when you get the 2 largest clusters. Remember that we were assuming a Euclidean case, but what about the non-Euclidean case? In this case, the only locations we can talk about are the points themselves. So there will be no average of 2 points. For example, let's say that in the non-Euclidean space, we have a cluster of points that form in this shape. And if we want to directly use the average of all the points to represent this cluster, it will be some artificial point inside the vacuum here, which makes no sense. So for the first question of how to represent a cluster of many points, we will use clustroids as opposed to centroid to represent the cluster of points. And we define the clustroid as the data point that is closest to other points. And for the second question, how do you determine the nearness of the clusters? We can just treat the clustroid as centroid, and then we will compute the intercluster distance as we usually do it. For example, let's look at a cluster of 3 data points, and the centroid of this cluster of 3 data points would be just in here. Basically, this is the average of these 3 points, and it's an artificial point. And it makes sense because it's in a Euclidean space. And the cluster of these 3 points will be here, because this is the point that is closest to the other 2 points. And note that this is actually an existing data point. And here we have different possible meanings of closest. One meaning can be the smallest maximum distance to other points, or it can also be the smallest average distance to other points, or it can also be the smallest sum of squares of distance to other points. For example, for some distance metric B, this term will be the square of the distance between a potential cluster and a data point. And we want to minimize the sum of the squares. Note that in terms of implementation of hierarchical clustering, at each step, we will need to compute the pairwise distance between all pairs of clusters and then merge them. So basically, it's going to take on squared time. And we need to run for on steps to merge all the points into one cluster. Remember that at each step, the number of clusters will decrease by 1. Therefore, in total, the complexity will be O and Q, and this is way too expensive for really large data points, really large data sets. Because remember, you want to compute the pairwise distances. Therefore, you will need to store a large n by n matrix. And for many data sets, it doesn't even fit into the main memory.